So let's show today is April 2nd, 2025, Wednesday, Physics 7, and let me fill you in regarding the schedule, right? I'm gonna share my screen and today, 2nd of April, right here, we're going to have lab 3, but we're also going to cover some of the material from some of the lecture, the first hour. I have to update the thing here because we didn't finish magnetic fields, right? So don't forget, next week we have no class meeting. It's going to be spring break. We're going to take time off, right? And after the spring break, we're going to have the exam, the Wednesday. Okay, 8:40. And by the way, it's 8:40, okay? If you, the previous syllabus that I had put incorrectly 8:50. So I am fixing that. Okay, that's why it's underlined here. Let's take a look at the notes. Let's see where we stopped. Page break. Let's see, we did the torque, right? Torque in a current carrying loop. Current carrying loop. That's what, and that's the step-by-step that I covered here. And we're going to start 21.7 in the book. And speaking of 21.7, chapter 21.7, right? Let's take a look there in the book. Anything here? Wild course resources. Okay, and that's the one we're covering. Okay. Right here. It's very important to remember this device, right? It's how we come up with an electric motor. That's how electric motors are built. And then what you're going to do now, magnetic field produced by currents. And that's another law of physics. So let's go get here to the notes. And I'm gonna copy and paste what we have here. Last time we finished section 21.7, 21.6. Which has applications to electric motors. Electric motors. Now I will introduce you to another law of physics. To another law of physics. And I'm trying to get the notes here from last year, so I can follow closely what we have here. Okay, so here you go. So sources of magnetic field, right? What produces the magnetic field? I discussed that with you before. What produces the magnetic field? What produces the magnetic field is the current. The source, what produces a magnetic field is a current, right? By the same token that electric charges are sources of electric fields, then electric current is the counterpart, is its counterpart for the magnetic field. Okay, by the same token that static charges are, but I'm not even going to say static charge, but the same token that charges are the source for the electric field, comma, its magnetic counterpart is produced by moving charges. Moving charges. Okay. And let's go. Oh, and there is a very simple experiment that we can perform. Okay, we remember that the compass, right, that the needle of a compass is something, the compass was something that was invented back in the 1200s, maybe even earlier than that, by the Chinese, and then the Mongols used. Marco Polo was found that out when he did his travels there in Asia. And the nice thing about Marco Polo, we usually grow up thinking that Marco Polo learned all that stuff in China, right? But that's not true. Marco Polo learned all that stuff in the Mongol Empire when Kublai Khan was still alive, right? Kublai Khan was the grandson of Genghis Khan. And that was the largest empire in the history of mankind, the Mongolian Empire. And Marco Polo had this opportunity to stay in the court of the Khan, right? Which was the kind of a king of that whole the whole land that extended from Eurasia to a little bit of from Asia until a little bit of Europe as well. Okay, and okay, so why I'm talking about the compass? Okay, I'm talking about the compass because it's in a way it's an old invention, and it was only around the 1700s. Okay, here you go. Hans Christian Ørsted. Okay, it was him who discovered that electric currents are the source of a magnetic field. So think about that. The compass was invented before the 1200, by the Chinese. But it took at least 500 years for us to discover that the electric current, was the source of a magnetic field. And how was that found out, right? How was that observed? Okay, the simple way to observe that, and that's an experiment that we can do in the classroom, is to put a bunch of compasses around a current carrying wire. And that's exactly what you have here, okay? This current carrying wire produces a magnetic field that circulates around the wire. And if this magnetic field is strong enough, okay, it will be able to bend the needle of your compass. And that's exactly what you see here. The needle of the compass, we find that it circulates around the current carrying wire, okay? And that's the direction of the needle is given by the right-hand rule. Let's write that down. And let me see if I have also we covered that, right? So here you go, the magnetic poles of the Earth, the magnetic force. We covered the magnetic force in a moving charge. And we also, this is the slide of the path of a moving charge in a magnetic field. I told you about the Crookes tube, the velocity selector, which is a very useful device that we can use to characterize the interstellar medium, for instance. Characterize the interstellar medium in terms of moving charges, in terms of electric charge. Here is another device that I didn't cover, is the synchrotron. And current carrying wire subject to B fields, we covered that as well. There's a magnetic force in a current carrying wire. Why is that? Because a current carrying wire is nothing but charges in motion, right? Once you get charges moving in a wire, it can be affected by a magnetic field as well. Here's another device that we didn't cover, is the Hall effect. Okay, talking a current carrying loop that we covered last time. Here's the loop. Okay, I'm differentiating several different arms of the loop, and depending on the orientation of the loop is going to oscillate, right? To oscillate with the magnetic field. And if we manage to invert the current at every half of a turn, we make the loop rotate in a single direction. Sources of B field, that's where we want to start talking about, right? Here you go. We have, I don't want to cover that. Let's see here if I have a better drawing here for you. Okay. Here is a current carrying wire. This current carrying wire, the current is moving from the left to the right in the positive X direction, okay? And what do we know, and you have to memorize that, is that the magnetic field circulates around a current carrying wire. And the direction of circulation depends on the direction of the current. And you use the right hand rule to find that out, okay? You put your thumb in the direction of the current and rotate, don't forget the right thumb, right? And rotate the palm of your hand. The direction of motion of the palm of your hand tells you the direction of the magnetic field. So here at the top, the magnetic field is coming towards outside the screen. And on the other side, the magnetic field is into the screen, okay? And let me get another one right in here. And the right way to illustrate this magnetic field is with this guy right in here. Instead of this point, right? Send back. Oh. Ow. Okay, now we have it. Magnetic field into the board. That's the direction of the magnetic field. It circulates around the current. Let's see if I have another illustration. Okay, here you go. That's what I wanted to show you as well. Suppose that the current is coming out of the screen, right? So the magnetic field at this point is going to be perpendicular to the position vector that starts at the electric current. Okay, that's one. And at another different position, you have this magnetic field. The magnetic field circulates around the current. That's what you have to know. Okay. And then let's write that down in the notes. Okay. The direction of the magnetic field depends on the direction of the current. Okay. The magnetic field always circulates around a current carrying wire, and its direction is given by the right hand rule, RHR. Okay. You direct the thumb to find out the direction, the proper direction, do the following. To find out the proper direction of the B field, you do the following. 1, you point the thumb of your right hand in the direction of the current. Okay. 2, move with the palm extended, right? With the palm extended. You move your palm as to close it. The direction of motion of your right palm is the direction of the magnetic field. Okay, that's how you find out the proper direction of the magnetic field. What about the magnitude? Okay, the magnitude, the intensity, right, of the B field, is always proportional to the current. Always proportional to the current. And don't forget, that's because the current is the source of the magnetic field. Right? So we can write down in the following way. Right, like that, proportional to I. But it is also inversely proportional to the distance from its source, right? So, and that happens to every field, right? The electric field is inversely proportional to the distance from the charges. The further the charge is away, this is weaker the electric field is. And also, the further a given point is from an electric current, the smaller is going to be the magnetic field. Okay? Can you memorize that easily? That's kind of obvious, right? You can just do the same analogy with a light source. The further away you are from a light source, the weaker is the intensity of your source. Okay? And we can even draw a parallel with the electric field as well. Here you go. The electric field is proportional to what? The charge, right? And another parallel with the electric field is that the electric field is inversely proportional to the distance, just like the magnetic field. Now, whether it's going to be, R to the first power, the second power, the third power, that's another question. That's another question, okay? And now we have the following laws. Okay. So here you go. Here the electric flux is proportional to the charge enclosed by an imaginary surface divided by epsilon naught. The flux of the magnetic field is always equal to 0, no matter what. And then we have this other law Lorentz force law. That's given by the charge, the velocity of the charge, and the sign of the angle of the velocity vector with respect to the magnetic field. And this new law that I'm telling you, that's Ampere's law, an electric current creates a magnetic field, right? An electric current is the source, even better, is the source of a magnetic field, which is given by Ampere's law. And what I want to add something else here to the magnetic field, right? What else? Well, remember that we say that the B field circulates around the current, whereas the electric field radiates away or towards its source. Okay? There's an important difference, but don't forget, I'm going to be very specific, the static electric field radiates away or towards its source. The static, oops, I meant this one here. The static electric field can remember that right here? Here is a illustration of the magnetic field circulating around the current. Let's see if I have another one. Okay, another one, a better one. Okay. And the further away we are, the weaker the magnetic field becomes. That's why this arrow here is shorter than this other arrow. And it is circulating in the counterclockwise direction because the electric current is coming out of the boards. Okay. How do I find the detailed? Okay, that's the qualitative treatment. Okay, that's the qualitative treatment. That's a qualitative treatment. And if they, for a very long, I'm going to give you the result without proving for now, okay? For a very long current carrying wire, okay? The magnetic field is given by the following equation. It's going to be a constant that I call a magnetic constant. It's the magnetic counterpart of the epsilon naught, okay? And I'm even going to put it in a different way. I'm going to separate the source and distance components from the constants, okay? Let's do it this way. So you can see, right? This term that you see right in here, I already mentioned to you before, right? I just didn't tell you the exact value, but now we have this constant and this mu naught, the magnetic counterpart of the dielectric constant epsilon naught, of the dielectric constant epsilon naught. And I'm going to give you the value of this constant. Is the magnetic permeability. Okay, magnetic permeability. That's the name of this constant. Let's see, what's the magnetic permeability? I want to know the exact value. It's not difficult to memorize. So let's see, here you go. Magnetic permeability of vacuum. Let's take a look at your book. Mu naught, permeability of free space as well, or magnetic permeability of vacuum. Here you go. Here's the value. Here's the 4 pi times 10 to minus 7 Tesla meter per ampere, okay? So where this value is given by copy and paste it. For pi, I want the times 10 to minus 7. Oops. And then, Tesla is, like I mentioned before, is the unit for the magnetic field. Okay? And we can go ahead and do some analysis of this equation to find out the unit, right? The units of this mu naught. 2 pi has no units whatsoever, but I has a unit. And in order for the magnetic field to have a Tesla unit, a unit of Tesla, we must divide this Tesla by ampere and multiply it by the unit of meter. Let's see. Okay? So if you substitute this mu naught right in here, we are going to get, by doing dimensional analysis, right? We get the units for magnetic field. Going back to here you go, Tesla, meter, amperes, right? Tesla, meter, amperes. Free space. Okay. That's the new, that's what's new for now, a new constant. And what else you have to know? Recall, that the parallel plate capacitor produces a uniform electric field, right? So we do also have a counterpart, a magnetic counterpart for the capacitor. Okay? And its magnetic counterpart is another device that you may have already heard of. It's the solenoid. We have solenoids in our car. Okay? What is a solenoid? Let me illustrate what a solenoid is. You go. A solenoid. Not this one. Is a cylindrical. Yeah, here you go. Here's a solenoid. That's how a solenoid looks like. Okay. It's a wire wrapped around a cylindrical tube. A cylindrical tube. And this device is so important that we call it a solenoid. And gives rise to that other important device that I mentioned to you before, right? Remember, well, the basic devices in electronics is the capacitor. First is the capacitor, then is the resistor, and then it is the inductor. The inductor is nothing but a solenoid like that. And other types of solenoids that you're going to see too. Other types of magnetic devices as well, okay? So that's how a solenoid looks like. And it produces a uniform magnetic field inside it. Can you remember that too? Okay? The electric field of a parallel plate capacitor is uniform, and the magnetic field of a solenoid is also going to be uniform, as I mentioned to you before. But don't forget, it's only inside the solenoid that it is uniform, okay? Only inside the solenoid. Don't forget what I told you. I told you that the magnetic field is always proportional to the current and should be inversely proportional to the distance from the current. But for the case of the solenoid, the magnetic field outside the solenoid is going to be 0, okay? So it's going to be, let's see, I'm going to here. Okay, let's put it this way. Outside the solenoid, the magnetic field is 0 up to the first order approximation. It's not exactly 0, but it's very weak. Okay, that's why I'm saying after the first order approximation. So here you go. I'm going to write that down. Be inside the solenoid. And what do we have here? We have the constant that you already mentioned. And this n, what this n is? This n is the number of turns of the solenoid. Okay? And the L that you see here is the length of your solenoid. So this little n that you see here is the number of turns per unit of length. Okay? Outside the solenoid, magnetic field is 0. So it is possible to derive that. Here you go. That's how we represent the solenoid in a simpler way. Current coming out of the board right here, wrapping around the cylinder and going into the board, right? Or into the screen. And we have several turns of this device at the end. And then we can do a lengthy derivation. Okay, so what do we discover? We discover that inside the solenoid, the field is uniform, and outside the solenoid, the field is 0. Okay? How do we calculate that? There is a way to calculate that. There is a way to calculate that. And the way to calculate that is by using Ampere's law. Okay, now what's the direction of this field? Again, the direction of this field is given by the right-hand rule. Okay, you point the thumb, there you go. You point, you orient your hand, right hand, in the direction of the electric current. You circulate the electric current with the right palm of your hand, and the direction of the right thumb is going to be the direction of the magnetic field. Okay. And just as a reminder, do you remember the electric field of a parallel plate capacitor, right? And just like the electric field of a parallel plate capacitor, we have the electric field inside is uniform, and the electric field outside is 0, right? Do you remember that? It follows a parallel with the magnetic field. And here you go, epsilon naught. It's like that. Okay. Let's make sure let's not forget what you see right in here is the amount of charge per unit of area, right? Per unit of area. That's what you see right in here. Let's make sure it's right? Electric field of a parallel plate capacitor. Sigma over epsilon naught. Exactly that, right? Sigma is the surface charge density. Epsilon naught is permittivity of free space. Okay. So just like that, we have, what do you have here? We have the Q that corresponds to, that is the electric counterpart of the current. And this A that you see right in here is this A right here is a geometrical parameter that corresponds to the length of the solenoid. And this mu naught here is the magnetic counterpart of the epsilon naught, right? This n is right in here just because of the number of turns of the solenoid that you have. If you have just one turn, n is going to be equal to 1. Okay? And but by wrapping up these coils several times, you end up producing a more intense field. That's the nice thing about the magnetic field. Just by increasing the numbers of loops that you have in your current carrying wire, you increase the current, you increase the magnetic field accordingly, proportionally, right? Just let's see, 2 loops is twice the magnetic field of just 1 loop. 3 loops is 3 times the magnetic field of 1 loop. 4 times, 5 times, 6 times, 7 times, and so on, okay? Okay, outside. For the case of the solenoid, the direction of the B field is given by the right-hand rule as well. In this case, you curl, you rotate, right? Instead of curl, you rotate your right palm in the direction of the current, and the right thumb indicates the direction of the B field, like that. How do I find? Okay, so now we have 2 equations for the magnetic field already. We have 2 equations for the magnetic field already. Okay, here you go for the very long carrying wire, current carrying wire, and the solenoids. How do we find out those 2 relations, right? How do we find out the 2 relations? Okay, to find the equation for the magnetic field of any current carrying wire configuration, we use Ampere's law. And that's chapter 21.8. And that's the basic equation that we have to use to find, which parallels, I'm going to explain which parallels Gauss's law for electricity. Which parallels Gauss's law for electricity, okay? So what's that? Okay, what do you have right in here? Instead of an area vector, now we are going to have a loop. See? So what we do? We create a loop enclosing a current carrying wire. Okay, and we multiply this loop by the magnetic field. We're going to do some examples and you're going to understand that, okay? And now we have, here you go, let's refresh our equations of physics, or laws of physics, right? This one here, and this one here. So now we can here write our laws of physics. This one doesn't change. Okay. This one just doesn't change. This one doesn't change, but this one is going to change. This one is going to be here written, and you have to understand what all those things mean, okay? And you will understand that just by doing some examples. What you see right here is the flux, and I'm going to here write, you have the magnetic flux and we have the electric flux. The electric flux is this one here. The magnetic flux is going to be this one here. Here you go. What we have here is the magnetic field parallel to the area vector. Here is the electric field parallel to the area vector. And here is the magnetic field parallel to the direction of the loop that encloses the current. Okay? Here is area. Here is a section of the loop, a section of the abstract loop. And we will be able to solve some problems. Let's see if I can do one example here. We still have time. Let's see. Okay. So let's see how to calculate the magnetic field. The first example that I'm going to do is that for an infinitely long wire using Ampere's law, okay? Infinitely long straight wire, let's put that, using Ampere's law. Okay, so we are going to look at the qualitative steps that we take before we solve for the magnetic field, right? Recognize that an element of current is the source of the magnetic field. The further away we are from the source, the weaker the magnetic field will be, right? So we're building just a qualitative solution of what we want to calculate. And I'm going to call that an example. Okay. And recall that the B field always circulates around the sources, according to the right-hand rule. Because it circulates around the source, you must use an imaginary closed path instead of an imaginary closed surface, like we did for the electric field, right? Like we did for the electric field. But recognize, just like in the case of Gauss's law for the electric field, recognize that Ampere's law applies only to problems that have symmetry. Okay? Just like in the Gauss law for electricity. And just like for the infinitely long straight wire. Infinitely long straight wire has a symmetry, provided you center your loop in exactly the wire. Okay, and what is the symmetry of the infinitely long wire? It's a cylindrical symmetry with an imaginary cylinder centered at the position of the wire. Since Ampere's law must, and let's not forget, Ampere's law must use a closed path loop. I didn't tell you that, okay? So, uses a closed path loop. Must use a closed path loop, just like the electric field that uses an imaginary closed surface, okay? Closed surface. That's the difference between Gauss law for the electric field and Ampere's law for the magnetic field. Then you must use a circular path of radius r around the wire to calculate the B field. Okay, so we have to illustrate that with the slides right in here. So here we go. Okay, right in here. Okay? That's an illustration of Ampere's law. And am I missing anything here? I think, let's see here. This one. Yeah, don't forget. Current enclosed by the loop, okay? Current enclosed by the loop. So I'm gonna give you some generic examples first, right? So here you go. So suppose that we have all those current carrying wires right in here, right? I1, I2, I3, okay? And I go ahead and come up with a very generic loop. I'm trying to calculate the magnetic field generated by those three wires here. If I choose my loop properly, I will be able to get the magnetic field. But if I don't choose my loop properly, I won't be able to get my magnetic field. Why is that? Because in this specific case, my loop is enclosing no current whatsoever. The enclosed current here is going to be 0, okay? And that's how we should use, right? And now if I decide to enclose all those three currents with this loop, what's going to be the enclosed current? The enclosed current is going to be I1, I2 minus I3. I3 is into the board, right? And I also have to choose the direction of the loop. In this case here, I choose a counterclockwise direction. A counterclockwise direction coincides with the direction of those two current carrying wires. That's why their sign is positive, but the sign of the other one is negative, okay? Now, if I go the other way, loop number 3, I have to change the sign of my sources of magnetic field. Okay, here you go. Here's the loop in the other direction, with enclosing two currents instead, because the direction of the loop I chose to be contrary to the direction of the current. I have the negative sign. Okay, and now we are ready to solve the problem for infinitely long wire. Okay, we start here with the current. Just one wire. We don't have two, we don't have three, just one. We are going to apply Ampere's law for a problem that has symmetry. This is one of the simplest problems that you're going to see for calculating the magnetic field, okay? So what we do next? Okay, we build an Amperian loop. We call it the imaginary loop around the current, and make sure this loop is centered at the current, okay? Okay, so here you go. Circular Amperian loop, which coincides with the integral path. It's not the integral path, but I don't want integral path. I want to put coincide with the path chosen, right? Chosen, like that. Next, if you do a loop like that, you won't be able to solve the problem because there's no symmetry in this loop with respect to the source of the magnetic field. Okay? Similarly, if the loop is displaced on the other direction, you won't be able to solve the problem because this does not represent a symmetric loop. So let's continue with the circular Amperian loop, which is centered at the wire. To make things simpler, I'm going to choose a direction of flow of the loop in the counterclockwise direction. Why is that? Because the counterclockwise direction coincides with the direction of the current. Okay? Next. Okay, because the counterclockwise direction coincides with the direction of the current, the magnetic field is going to be counterclockwise as well. And tangent to this pass. Okay. So we have, let's say, 40% of the problem solved for now. Okay. And let's go back to, oh, not this one right here. Let's see here. Okay, it moved. Must use a closed path, just like the if field, right? They must use a circular path of radius, and we have a radius r here. The loop has a radius r from the center of the source. What's next? Now we apply Ampere's law. And let's see how we are going to apply Ampere's law. Okay, so here you go. That's how we're going to apply Ampere's law. And by the way, for this specific case, n is equal to 1 because we have just a single pass. Okay? So what we end up having is going to be something like that, like the following. We have only one circular pass. Here you go. So it's going to have magnetic field parallel to the pass chosen, to the circular pass chosen. Going back here. Let's go back here. Here you go. Magnetic field is going to be parallel to every point along this path. Why is that? Because the path chosen will also be tangent to this circular path. Okay? And then what we're going to do, you know, from item 2 above, we found that B is tangent to the path, so the magnetic field coincides with the magnetic field that's parallel tangent to the path. The current enclosed by the Amperian loop is I. Okay, there is just one current being closed there. You do not have multiple currents. Consequently, what I'm going to replace I enclosed by I. And then we have to determine this multiplication factor here. Okay, what is it going to be? This is not going to be, you know, just remember that the full pass around this loop is going to be given by the circumference of this loop, which is 2 pi r, right? So here you go. Delta L is going to be 2 pi r. Consequently, substituting delta L in terms of r, we get something like that. And now we finish our solution and get exactly what I told you it was supposed to be. Okay? Mu naught I 2 pi r. Remember I told you that? Recall what I wrote down before, right? Here you go. Right in here. It's exactly the same solution. That's how we find the solution here. By using Ampere's law. 1042. Okay, I think it's a good point to have a break. Let me take attendance. And while I take attendance, I'm going to also upload your lab report. And I'm going to stop sharing my screen here momentarily. Remind me when I go back to this screen, okay? And as you answer the attendance, I will upload your lab tree. Today is the second lab. Let's see, 26. Yeah. Erase that. Ish. This one. Insert that cell, okay? And I stop sharing the screen, right? Isabella is trying to get in. Now let's take a look. Let's see here. Bear with me. Lab number 3. Don't forget lab number 2 is due today, 11:59 p.m. Okay. Report for lab number 2. And we are going to do lab number 3 today. Okay. And I'm going to get something else here. Excellent. Raw data. Good. Let's start with Abir Ahmad. Are you there, Abir?
Yes.
Okay, thank you. And then I'm going to upload your spreadsheet. Yeah, I'm doing attendance right now, Galia. Let's see here. Okay, I uploaded your lab, your third lab report. Next, here is Nestor Alvarado. Are you there, Nestor? Doesn't look like Nestor is here, right? Yeah, it doesn't look like Nestor is here. Next in line is Monte. Are you there, Monte?
I'm here, Professor.
Okay, thank you. So I'm going to upload your lab report, your spreadsheet. Oh, wait a minute. There's something incorrect here. Oh gosh. Let me do that again. Submit for student. It looks like I upload your, let's see, Amber. Abir, right? Here you go. Let's see. Oh, okay, now you have it right. Now let's do that for Amber, for Monte. Student. Monte, okay, good. You have your spreadsheet there, Monte. Next, Monte. Well, you know what? Let me take attendance first, and then I do the uploading. Okay, Isabella, are you there, Isabella?
Here.
Okay, thank you. So I'm going to Justus Bolden. Are you there?
Professor, are you able to hear my mic? I think it's working now.
What's working now?
The previous time that was in class, I think last week, like my mic wasn't working. I just like wanted to see
Ah,
if it's like working now.
okay. Yeah, I can hear you loud and
Cool.
clear. Okay, so
Thank you.
Alexandra Burmistrova, are you there,
I'm here,
Alex?
Professor.
Thank you. Now, Benjamin Carvajal, are you there? Thank you, Benjamin. Elizabeth Castellano. Let's see if Elizabeth is here. Okay, thank you, Elizabeth. Next is Natalia Cordoba.
Hi, I'm here.
Thank you, Natalia. Jacqueline Delgadillo. I don't see Jacqueline. What about Jenny Diaz?
Here?
Thank you, Jenny. Valerie Diaz.
Here.
Thank you, Valerie. Juan Escalera. I don't see, okay, looks like Juan is here, right? Hello, Juan. Okay, thank you. Next is going to be Bianca Eulaki.
I'm here.
Thank you, Bianca. Edwin Gonzalez. Thank you, Edwin. Next is Eli Gonzalez.
Here, Professor.
Thank you. Manuel Hernandez Pineda. Hello, Manuel. Okay, I'm going to put a star here on Manuel's attendance. Samantha Hubert.
I'm here.
Thank you, Samantha. CJ Hutton. Hello, CJ. I can't hear from CJ. I'm going to put a star here in his name for now. Luis Leal, are you there, Luis? I don't see Luis either. Amber Lopez. Are you there, Amber? I see Amber listed here, but I don't hear from her. Putting out Arely Lopez.
I'm here.
Thank you, Arely. And next is Genesis Lopez.
I'm here.
Thank you, Genesis. Mary Michaelian. Are you there, Maddie? I see Mary here, but I don't hear from her. I'm gonna put a star here. Galia. Galia's here, right? Thank you. Ramon Olivares. Are you there, Ramon? Yeah, I don't see Ramon here in my list. Taylor Thorne.
I'm here.
Thank you. And next is Jeremy Pittman. I don't see Jeremy. Stephanie Ramos.
I'm here, Professor.
Thank you, Stephanie. Leslie Rios. Hello, Leslie, are you there? Okay, I can't hear from Leslie. I'm going to put a star in her name. Next is Jason Strait.
Here.
Thank you, Jason. And last but not least, Gema Torres Navarro.
I'm here, Professor.
Thank you. Let's see how many students we have. 22. We have 27. 5. 1, 2, 3, 4, 5. Okay, I want to give opportunity again. One. Manuel Hernandez, are you there, Manuel? Hutton, right? Okay, CJ Hutton. Okay, thank you, CJ. And what, Manuel? I don't hear from Manuel. Amber Lopez. Another opportunity here to answer me. Okay, don't hear from Amber. Mary Michaelian. Okay, I don't hear from Mary. And Leslie Rios. Are you there, Leslie? Okay, now I don't see Leslie in my list. Okay, so let me put it as 0 here. Okay, 3, 6, 26. Leslie. Oh no, Leslie is here. So it's in my list, but I don't hear from her. Okay, okay, thank you, Leslie. Okay, 24. Okay, now I'm going to upload the spreadsheets, okay? Let me. Who's trying to join us? Leslie, okay. Estourou. Jacqueline Delgadillo. Jacqueline Delgadillo, are you there? No, I don't see Jacqueline Delgadillo. Next, Manuel Hernandez. Okay. Manuel Hernandez. Next is going to be Amber Lopez. Okay, another opportunity, right? Luis Leal, we need here. I don't see Luis Leal. Ramon Olivares. Next, Jeremy Pittman. Okay, everybody else is gonna get. Luis. Okay, now. So Amada Beer may have already the spreadsheet, and so does Monte Bastian. Now is next in line here, Isabella Ballesteros. I'm uploading your spreadsheet, Isabella. Just checking there. Next. Now is Justin. I'm going to upload your spreadsheet, Justin. Next. Alexandra. Check if you can download your spreadsheet, Alexandra. Benjamin Carbajal. Elizabeth Castellano. Next is Natalia Cordoba. Jenny Diaz. Let me make sure. I'm checking my spreadsheet here before continuing upload, okay? I want to make sure everything should be okay here. Leslie. Okay, so now let's go for Jenny Diaz. What's going on here? Let's see if I can get it. Huh, something wrong here. Let's see what's going on. Oh yeah, I know why. Okay, now it should go. Good. Okay, Jenny, now you have your spreadsheet. Next is Valerie. Valerie, you have your spreadsheet there. Who's trying to join us? Nestor? Mr. Alvarado? Bianca? Next. I'm Eli Gonzalez now. Let's see. Manuel Hernandez, are you still there? Are you there, Manuel Hernandez? Okay, Manuel Hernandez still didn't show up. Samantha, I'm uploading our spreadsheet. Next, CJ Hutton, it's your turn now. I'm uploading our spreadsheet. Arely, okay. Next, Genesis. Mary Michaelian, are you there, Mary? Yeah, it looks like Mary's not here. Galia is here, right? Check your spreadsheet, Galia. Ramon. Taylor. Next is Stephanie. Next is Leslie. Going straight. And now let's see, last hammer. Okay, hang in there, Elizabeth. I'll check what's going on. Elizabeth Castellano, right? Let's see, Elizabeth Castellano. Yeah, it's what happened? Yeah, it shows here that I uploaded. Try to refresh your screen, Elizabeth, and see if it appears. Okay. Let me know. Okay, I already uploaded the spreadsheet for everyone. Let me know if you did not get it. Okay. And 11:03, let's see. Wanna hear from the other students? Does anybody else, in addition to Elizabeth, didn't get the spreadsheet? Natalia Cordoba, right? Let's see, Natalia. Okay, well, it also it shows that you did get it. Okay, let's. Did you? What about yours, Elizabeth? Did it show up already, or you still cannot download it, Elizabeth? You got it. Okay, Elizabeth got it. Okay, so wait a little bit, Natalia. Maybe it's gonna show up. Nestor. Okay, Nestor. Let's Nestor Alvarado. Right. So let me upload that here for Nestor. And let me give you attendance for Nestor. Anybody else who didn't get it? Let's take a break, right? Let's see, Natalia, I have it now. Okay, thank you, Natalia. Let's see. Jacqueline Delgadillo, let's see. I don't see Jacqueline Delgadillo here. Manuel Hernandez, are you there? Manuel is in my list, but he must be away from the computer. Amber Lopez. Hello, Amber, are you there? Okay, I don't hear from Amber. And Mary Michaelian, are you there, Mary? Okay, so let's take our break now. It's 11:05. Break from 11:05 a.m. to 11:20 a.m. Okay, let me just flash my screen here for you to see. Screen 3. Here you go. 11:05 to 11:20. And so let's take our break now, and then we come back in 15 minutes. See you soon. Bye bye. I am back here. Okay, so we are back here, and now we are going to do lab number 3. Mary, right? Let me upload your spreadsheet, Mary. Let me stop sharing the screen momentarily. Here, Mary. Let's see. Okay, uploaded your spreadsheet, Mary. Let me know if you do not have any spreadsheets. And so what we're doing today is lab number 3. Get my notes here for lab number 3. Huh, strange. Okay, good. So what we're going to do today, we're going to do resistance measurements. And I'm going to copy and paste here at the okay, so okay, you already know about the digital multimeter that I introduced before. Okay, so it's called multimeter because it can measure several different parameters. Okay, so you already know that we can measure voltage. We covered that before. And the next measurement that we are going to do is going to be the resistance measurement. In addition to the, oh, let's see, I want right here, resistance measurement. As a volt, whenever the ammeter, the digital multimeter measure voltage, we call it a voltmeter, right? Whenever we measure resistance, we call it a ohm meter from the unit of measurement ohms, unit of measurement for resistance. And then you can measure other things too, depending, you can measure a multimeter, you know, a very basic multimeter is going to measure at least those three parameters: voltage, resistance, and current. But then there are some fancier multimeters out there that will be able to measure capacitance, frequency of a circuit, and electric field as well, okay? So what we're going to do, what do I usually do, right? I usually provide my students with 6 different resistors. And let me show you, I guess I showed that to you before. If I haven't, let me show it again. Let's see here, resistors, Wikipedia. Here you go, resistor, here you go. That's how resistors look like. I believe I already showed that to you. But there are small devices that are mass manufactured. You can buy them. You have small and large resistors, okay? You have small and large resistors, but the most commonly available is this one here that this size without the leads. Those resistors, they all come with this color code that you see here. And this color code is a code that's used to determine, to tell you what the resistance of the resistor is. Okay, at the time that we didn't have multimeters widely available, we used this color code to tell the resistance value of the resistor. Nowadays, we have multimeters and they can determine the resistance rather, easily. This symbol, that's the symbol that I introduced to you for the resistor, but we also use this symbol here as well. Okay. Here are different resistor sizes. Okay, you can have an idea of the sizes of different resistors. Here is another resistor here. And then, look at the size. We have a ruler here on the side in centimeters, shapes and size. And then we have even smaller than that, believe me. You have even smaller resistors than that. Okay? So going back to my notes, provide my students, after experiment in the class, I do the following. Provide the students with 6 different resistors. So let's gotta do a list of the materials, right? List of the materials. List of equipment and material. 1, 6 resistors of different values. That's one. Digital multimeter to measure resistance. What else do we need? Okay. I'm going to show you a spreadsheet here so you can follow. Here you go. And here's this spreadsheet that you all have. Okay, so I provide 6 different resistors to my students. And I provide a multimeter too. Like I said, each resistor has a color code. And I provide, all those 3 columns here, they're related to the color code or the nominal value that we have, okay? We usually my resistors usually have 4 codes, 4 color codes. The first digit represent the first color represent the first digit of the resistor, of the resistance value. The second color and represent the second digit of the resistor value. The third color represents the multiplicative power that you have to multiply for the resistance. And the last color represents the percentage difference that the manufacturer have for the resistor itself. Okay, so going back, I'm going to document all of that for you, and here you go. Right in here are the colors, right? So you see we have 4 color bands here. The first color represents the first digit of the resistance, the second color, the second digit, and here you represent the power, the multiplicative power of the resistor. If this color represents number 2, right? Those 2 colors should be multiplied by 100. And this last one here represents the tolerance, okay? The tolerance of the resistance, usually like 5 or 10%, okay? That's what it is. And all those colors, let's see if I can get the numeric value of those color codes of resistor. We gotta go to the internet. Color code. Is this accurate? Let's see. Yeah, this 1, 2, 3, 4. Yeah, there's wait a minute. Tolerance. They have a third one here. Yeah, there are some resistors that come up with 5 colors, by the way, okay? This one has only 4, okay? There are some, but the resistor that we use comes only with 4 colors. But there are resistors out there that are available in the market that are gonna have 5 colors. Like this first, the second, this third, then the multiplier factor, and the tolerance, okay? The tolerance depending on the color of the tolerance, you can have anything between 1% and 10%. Okay, so here you go. Here's an example of 1, 2, 3, 4, 5 color code resistors. But the one that more widely available is this one, is only 4 colors. And here are the numeric value for each color. Black is 0, brown is 1, red is 2, orange 3, and so on, right? For the multiplier, we have something similar. Well, what is different is the tolerance. The tolerance, we have 1% for brown, 2% for red, 5% for gold, and 10% for silver. Okay, so so I want you, just as an exercise, determine what would be the color. Oh, this one already has it. Okay, here you go. Brown seems like red to me, right? Red or orange? Yeah, it's red. It's red. The multiplier factor is the brown as well, right? So here you go. Brown. Brown represents the number 1. Red represents the number 2. So you have 12. The multiplicative factor is the brown, which is a power of 1. So it's 10 to the first power. So it's 12 times 10, 120 ohms. That's why he wrote down 120 ohms, okay? The tolerance is what? The tolerance is silver, is gold. Okay, it's a gold color. So what this tolerance means? This tolerance means is that the manufacturer can guarantee a resistance value between 120 minus 5% and 120 plus 5%. Okay, plus and minus 5% is 6 ohms. So it's 120 minus 6 ohms, which is 114. and 126. The manufacturer guarantees that this resistor has a value between 114 and 126 ohms, okay? That's how this color code works. Thank you, Ellie. So yes, it's a good one. You can also, color code for resistors, right? You can go in the internet. You're going to see all sorts of tables out there. Okay, so let's write that down. Digital multimeter to measure resistance. And okay, so in an actual experiment, I do the following: provide my students 6 different resistors. The student used 2 different methods to determine the resistance of each individual resistor, using its own color code. Okay, and again, the color code, the nominal value, right, of the color code goes right in here in this column. The lower value of the tolerance goes right in here. That's minus whatever percent you have. And here's the plus whatever percent you have. Okay. The color code provides only 2 significant digits, right? Only 2 significant digits. 4, and by the way, 4 color codes. And let's see here. Oh, I have this step by step here. A few out there have 5 colored band. The color of each band represents a number. Okay. The first color represents the first significant digit of the resistance value. The second color represents the second significant digit of the resistance value. The third color represents the multiplicative power in the base of 10 of the resistance value. And the fourth color represents the tolerance of the resistor, right? And here I have an example. Yellow, violet, orange, silver. Yellow is 4, violet 7, orange is 3. Silver is a tolerance of plus and minus 10%. 47 times 10 to the third power, which is 47,000 ohms, and 10% would be, 10% of 47,000 would be 4,700. 4,700, okay? Now, what most widely used today, we moved away from use those color codes because nowadays we have digital multimeters that are very accurate and very inexpensive, right? And then also can provide with a larger number of significant digits. So we use the multimeters to do that. And the number of significant digits you can find out from that table that I provided to you before. Let's take a look at the table. I provide to you at the beginning of the semester. Significant digits right here. The number of significant digits varies from multimeter to multimeter, right? But this one here, that is this table that you see here, is for the multimeter that we have there at the college. Here you go. You gotta look at the table. Resistance. Okay, that's the table that you want to concentrate. Okay. And the number of significant digits depends on the value of the resistance. Anywhere between 1 ohm and 9.99 ohms is 3 significant digits, right? 10 and 99.99 is 4, 5, 4, 5, depending on the value. Okay. So here in this case, the DMM, I have 8,059 ohms here at the top. Okay. And let's take a look at the color code. 8,059 should be this one right here. You're supposed to display it with 4 significant digits. Okay. As an example. But so here you go. You already know here should be 2 significant digits, right? Here 2 should be 2 significant digits and 2. And here the number of digits is going to depend on the value of the resistor. And we have a table here is the percentage difference between the nominal value and the measurement of the digital multimeter. I want another spreadsheet. I want another PowerPoint slide here. Let me get that. Lab. Illustrations. Not this one. Lab slides. Resistance measurement. Here is a multimeter, a very large multimeter, right? That we have, and we are going to use also. What else are we going to use? We are going to use a prototype board that's available out there. Okay, we're going to connect our resistors in series and in parallel. So let's put the prototype board in our list as well. List. Prototype board to connect our resistors in series and parallel. Okay. Wow. We have we hear the noise here in the background. We have someone doing some serious work here in the apartment. Okay. I want to know if everybody got the spreadsheet. Let me go one by one. Wow. Let's hope it doesn't get too noisy. See here, download spreadsheet. Spreadsheet. Abir, did you download the spreadsheet?
Yeah, I was.
Okay, thank you. Nestor, did you manage to download the spreadsheet?
Yeah, I did.
Okay, thank you. Monte, did you get your spreadsheet? Is Monte here? Yeah, I don't see Monte here. Huh? Monte and Barshian. Okay, so here you go. I'm gonna write that down that he left. Isabella, are you there? Did you get your spreadsheet? Isabella. Hello, Isabella. Okay, I'm gonna put a star here for Isabella. And Justus, are you there? Okay, you got it. That's good. Next, Alexandra Bamistrova.
Yeah, I have it open.
Good, thank you. And Benjamin Carbajal. Did you get your spreadsheet? Got it? Oh, wait a minute. Yeah. Next is Elizabeth Castellano. Okay, thank you. Next is Natalia Cordoba. Good. Next is Jacqueline Delgadillo. Did she came in? Doesn't look like she came in. Okay, next. Jenny Diaz. Did you get your spreadsheet, Jenny?
Yes, I got it.
Okay. And Valerie Diaz.
Yes.
Okay, thank you. Juan Escalera. Thank you, Juan. Bianca Eulaki.
I got it.
Thank you. Edwin Gonzalez. Hello, Edwin. Okay, I don't hear from Edwin. Let's go to the next one. Eli Gonzalez, did you get your spreadsheet?
Yes, I got it.
Okay, thank you. Manuel Hernandez. Hello, Manuel. Doesn't look like Manuel is here. Okay, now looks like he left completely. Okay. Next. Samantha, did you get your spreadsheet, Samantha?
Yeah, I got the spreadsheet.
Okay, thank you. Can you open it too?
Yes.
Okay, good. So next, CJ. CJ got your spreadsheet, right, CJ? Okay, thank you. Luis Leal is not here. Okay. Amber Lopez, you get your spreadsheet, Amber? Can you hear me, Amber? Okay, I'm gonna put a star here on the Amber's name. And Adelie, are you there?
Yes, I already downloaded it.
Okay, good, thank you. Genesis, did you get a spreadsheet?
Yeah, I got it.
Thank you. Mary?
Yes, I got it.
Okay, thank you. Galia? Hello, Galia, did you get her? Okay, good, she has. Thank you, Galia. And Ramon Olivares? Ramon, okay. Yeah, I don't see Ramon here. Okay. Next is Taylor Farm.
Yeah, I downloaded it.
Okay, thank you. Jeremy Pittman. Jeremy is not here. I need it, Professor. You called my name already. Okay, Edwin, right? Edwin, let's see. What's your last name, Edwin? Okay, Gonzalez. Okay, so you did get your spreadsheet, right, Edwin? Yes, I have it. Okay, Amber. Okay, thank you, Amber. And Amber Mary, attendance here and why? Edwin. Okay, next, Stephanie Ramos. Did you get your spreadsheet, Stephanie? Good. Next, Leslie Rios. Did you get your spreadsheet?
Yeah, I got it.
Thank you. Jason Strait.
Yeah, I got it.
Good, thank you. And Hema Torres Navarro. Did you get your spreadsheet, Hema? Doesn't look like, okay, Hema is still here, right? Okay, she's not answering. Let me put a star under her name and lab 3. Good. One more column here. And here's I'm gonna give you an example how you, unfortunately, I do not have a resistor here with me to show you, but let me stop sharing the screen so you can see how we do the measurements. Here's my multimeter. Let me stop. Okay, here's my multimeter, okay? And it can measure all sorts of things, voltage AC, voltage DC, okay? Resistance measurement is down right in here, okay? It shows a ohm symbol, omega symbol, capital omega for the symbol of ohm. And then I have those two probes, one connected to the positive terminal of the multimeter, the other connected to the negative terminal of the multimeter. Okay, so here you go. The red goes to the red, the black goes to the black. Okay, and if I want, I can measure the resistance of almost anything, okay? I can measure the resistance of this pen, for instance, okay? Every object is gonna have a resistance. I can measure the resistance of this piece of paper. What I have to do, I have to, get one side of the probe, make contact with one point of my paper, and the other probe contact with the other point of my paper. So every object has a resistance value. Okay, paper, for instance, is not used in electrical circuit, but it does have a electrical resistance value. Okay, and right now I'm reading overload because the resistance overload like that. Oh well, because the resistance is too high for the multimeter to display it for me. Okay, this is a dielectric material; it has a very high resistance. My pen too has a very high resistance because it's another dielectric material. It's a plastic. if I touch one probe to this middle of my pen and the others another position here, I'm gonna get also an overload measurement, okay? Because the resistance is very high. However, if I get a metal to measure the resistance of a metal, here you go. Here's my scissor, okay? Let's see what do I get. I'm going to, unfortunately, I don't have a resistor here. But if you're gonna get a resistor, a real life resistor, all you have to do is touch the extremities of the resistor with one probe and the other, okay, simultaneously. So let's see here this scissor of mine. Okay, my scissor has a very low resistance. I can read it here, 0.17 ohms. Okay. It's going to be difficult to display that for you, but let's see. You have to believe me. That's unless I put it here. Let's see. No, I'm going to try to raise the height of this. No, we're almost there. Not there yet. Here you go. Okay, now we have it. Now you can see OL, right? OL for overload. But then when I measure the resistance of this metal scissor, because the scissor is made of a metal, the resistance of the scissor of this metal is going to be very low. In this case, let's see what's the resistance. Is 0.22 ohms, which is a very low resistance. Actually, it varies, right? From 0.17 to 0.22. Now it's 0.16. Let's go further away. The longer the distance between the probes, the more should be the resistance. Now let's see. Now if I touch the metal, one probe in the metal and the other probe in the plastic handle of the scissor, now the resulting resistance is going to be a little bit higher, because now we're combining not just a metal with a plastic, with a material that is a dielectric. Okay, here you go. Okay, metal right here and plastic down here. And I'm getting 4.6, 4.4. It's increasing. It takes some time to stabilize, but it looks like it's around 5, maybe 5 amps, 5 ohms. Okay, that's how we measure resistance value. It's very straightforward, the measurement of resistances. Okay. And then let's go back to my spreadsheet, right? Not this one right in here. And then now I have to share my screen with you. Do you have an idea now how those measurements are made? It's very important to know how to make this type of measurement, okay? Here you go. So, and you gotta put all the units here, right? And the units for the percentage difference. And here you have all the measurements. What you're going to do next, you have those measurements, then you have to worry about significant figures, right? But the first thing that you have to do, is to plot some graphs. Okay, and let's see what those graphs are. There will be more than one graph. Okay. Let's go as a result. Plot nominal value along the x-axis and the DMM value along the y-axis for the following tables. That's the first plot. Okay, so we are going to see how close the nominal values is to the measured values of the resistor. Our first graph, this should be the plot of table 4-1. Here you go. This one and this one right here. Okay, can you do that? Let's start with the most fun part, right? That is just plotting the graph. Unfortunately, the values that I provide my students for this table, they are very far away from each other. That's why you have a bunch of points concentrated here and then a lonely point right here. Just not well chosen, just my mistake, okay? This point here is around 9,000 ohms. And this other one here is just 300 ohms. That's why you have this huge gap here, right? And then what you're going to do next, highlight all the data points. We have a total of 6 data points. Add trend line, display equation chart, display R-square value chart, okay? What this graph is telling us, very important. Because the values of the nominal resistance is supposed to be close to the values of the resistance measured by the multimeter, this slope here is going to be very close to the value of 1. It's going to be very close to 1, okay? And it is indeed, it's only 2% off, 0.98. You should get values like that for the slope. And for the R-squared, it's going to be very close to 1 too, but I want to put more decimal places there. Format trend line label, right? I wanna see a number that's not 1, but a number close to 1. In order to do that, we have to increase the number of decimal places. I put decimal places there, 5 decimal places there. I still didn't get a resolution. Let's put 7 now. Yeah, now I got it. See, this number is so close to 1 that we have to add 7 decimal places to see an R-square that's different of 1. Okay? So that's my first graph that you have to plot. That's the first graph you have to plot. The resistors are just single resistors. They are not in series nor in parallel. Okay? Resistors in series and parallel is that what you're going to do in the next other 2 graphs. Okay, so here we go. The first, so we use this device, the prototype board that's used to build circuitry for your experiments. And the way you connect those 2 resistors in series, you can either do by your own hand, okay? Or you can use the prototype board. I prefer to use the prototype board because it's not your hand is not as steady as the prototype board is. When I plug this, and let me show you a prototype board too in the internet. Prototype board. Prototype board. Okay, that's how they look like. There are a bunch of sizes. They are full of holes. Those holes are used to insert the resistor into them. Okay? Very similar to what I did here. If you insert one resistor in this column and the other resistor in the same column, they are connected. It means that those 2 leads are connected, electrically connected to each other. Okay? And what are we going to do? We're going to combine resistor 1 with 2, resistor 1 with 3, 4, 5, and 6 in series. And you're going to end up having five data points in the graph. Okay, here you go. Highlight it. And here, right in here for the nominal value, what am I doing for the nominal value? I am summing up the resistance 1 and 2, summing up the resistance with 1 and 3, and so on, okay? Don't forget to display them with the proper number of significant figures. Here we are measuring. Here we are measuring, here we are calculating. And when we highlight those two, we learn that, yeah, they behave rather nicely as expected, right? Add trend line, display equation chart, and look here. Again, we have a slope that's very close to 1, which proves, right, that our theory of combining resistance in series reflects real life. Don't forget, here is the measurement with the multimeter, and here is the summation between the two resistors of the resistance values using the color code. Okay, by using this configuration right in here. I connect one end of the multimeter to this lead and the other end of the multimeter to this other lead here to measure the equivalent resistance. Here is the resistors in parallel. Okay? And then we connect my multimeter probes to those two leads. And that's going to be my next graph, resistor in parallel. And what you're going to
Professor,
do-
I have
Yeah?
a question. I'm sorry.
Yeah.
I'm having trouble. I don't know how you grabbed because you know how they were side by side the first plots? Like how did you grab them to graph them? Because I only lets me grab them if they're side by side. So I'm like
Okay.
struggling to do it.
Okay, I can help you. Here you go. Let's go back here. Right? You're talking about the first graph, right?
Yeah.
Okay. So you go ahead and highlight here, right? That you can do easily, right?
Yeah.
Okay. Now the trick here is how to highlight this other one without you know, turning off the other, right? That's the trick. So what's the trick? If you're using a PC, you press the control key in your PC, and then you highlight it.
Oh, okay.
Okay. You're using a PC or a Mac?
Oh, I got it. It was a PC.
A PC, okay.
I stopped using my Mac because I don't know how to do the other ones on the Mac.
Okay.
Okay, I got it.
So now you can plot it, right?
Yes, thank you.
Just press the control key. And okay, so let's continue here with the and what we're going to do, just you know, for resistors in, let me show you the equation, right? Okay, let me show you the equation. This one that I want. Okay, that's the equivalent resistance, right? So let's say this one here is the measurement of the multimeter. And this one here is the summation that we get for the nominal value, the color code value, okay? So we have our, I'm gonna put it here, equivalent 1. We're gonna make a total of 5 measurements for the resistors in series, right? R1 with R2, R1 with R3, R1 with R5, R4, sorry, R4, R1 with R5, and then R1 with R6. Okay, don't forget what this one here is the measurement with your multimeter, and those 5 ones here are the summation of the color-coded resistors And those are all data points in your graph, a total of 5 data points in your graph, right? In a more generic sense, here you go. I'm gonna write it down in a more generic, in a simpler way. Oh, what's going on here? I don't want, here you go. I, right? I plus 1. I plus 1. Oh, not what I want. Here you go. That's the notation that I am adopting just to, instead of writing down all those 5 equations, okay? I write just a single equation to represent all those 5 equations, right? If I am, and by the way, we gotta say too that I from 2 to 6. No, let's see, from 1 to 5. From 1 to 5, okay? Note C that every data point that we have here has the same value for R1, right? And what is your variable? Your variable is this one right in here. If you are going to write down in terms of an equation, okay, in terms of X and Y equation, we can write it down like that, you know, Y is equal to R1 plus X, right? That's how we could write that in terms of an equation, a linear equation. It's linear in X, and it has a slope that's equal to 1 and an intercept that's supposed to be equal to R1, right? Let's see if it matches. Here we go. The intercept that I'm getting here is minus 49. Yeah, let's see. And R1 is going to be, yeah, it didn't match nicely, unfortunately. Yeah. But the slope, at least the slope, we got it. Okay, why is that? You know, there might be something related to the values of the, let's plot it again. I'll just insert, let's see, trend line. Yeah, unfortunately, the slope that doesn't coincide with R1, yeah. But that's because of the slope, no, the intercept, right? But you don't have to worry about that. We have to worry about just the slope. The slope, we get a good value. What about the resistors in parallel? For the resistors in parallel, we have to be careful how we plot this equation, okay? We cannot plot, you know, R of the multimeter versus the R nominal, okay? We have to do something else. We have to remember that the equation is something like that, right? And just like before, I'm going to, here you go, right like that. My first point, right? My second point in the graph, my third point in the graph, my fourth point in the graph, my fifth point in the graph. And just like before, we can here write that in a simpler way. The difference here that we have to raise to the negative power. of 1. Like that. Here you go. This one is going to be negative power of 1. And I'm going to call the inverse. Let's see how I'm going to do that. Okay, that's going to be I plus 1. I plus 1. X is in this case is going to be the inverse of the resistor I plus 1. Okay, and the intercept is supposed to be the inverse of R1. Let's see what we get. This slope we're supposed to get 1, right? So let's see what we get here. Here you go. Plot the inverse measured by the multimeter and the summation of the inverse of the nominal value. Insert chart. Here you go. A big gap as well, right? Must be the big gap that's giving that problem, the difference with the intercept. Trend line, display equation chart. Here you go. Like that. See that the slope is very close to 1, right? Don't forget to put the units. So we have all those 3 graphs. All the 3 graphs we want. Is giving us an intercept of 0.0002. Right? Let's see. 0.0002. 0, 1, 2. It's 2 times 10 to minus 4. Okay, which is, kind of close to this one. Looks like it's close with this one, okay? Closer than the other, but it's still not on the money, not in the money, right? So those are the 3 things that you have to do initially. Fill up, and then, you're plotting all those 3. Let's see, resistor in series. I'm gonna do like that. I'll put this one. I'm going to put right in here. Because the resistors are in series. Here the resistors are in parallel. For 1, 3, and 4. And then we gotta fill up table 4-2. Let's see what's table 4-2. Table 4-2 is this one right here. We're just going to repeat, okay, what we did before, number of data points, the regression equation, and the R square value for a single resistor, resistor in series, resistor in parallel, and the CL for each combination here. Okay, and what we have here, okay, then we have the percentage difference. But logging on the slope, you don't have to log the intercept. Okay, 12:15 already, huh? We need to take a break. Let's take a break. We have let's take a break now, and here you go. Break from 12:16 p.m. to 12:31 p.m. Okay? So I see you in 15 minutes. Do I have any questions before you go to the break? Start with the 3 graphs, right? And then we worry about the rest. I see you in 15 minutes. Okay, right here, and so I'm back here. So I want to know if you have to plot the first, second, and third graphs, okay? Graph 1, 2, and 3. Graph, third graph. So Abir, did you manage to plot the first graph? I don't see Abir here. Okay, and now Nestor, have you plotted the first graph?
Yeah, I did.
Okay, what about the second and third?
I'm on the second. I'm
Okay.
finishing up the second graph.
Okay, you're working on the second. Okay, good. Monte, do you have any questions on Nestor?
No, I don't. I'm just
Okay.
following along.
Okay. Monte, Ambarshan, did you plot the first graph? Monte's not here, huh? Okay, left. Huh? Next, Isabella, are you there? Did you plot the first graph, Isabella?
Yes.
Okay, what about the second?
Yes.
Yes, and the third?
No, not the third yet. I'm working on it.
Okay, good. Thank you. Justus Bowden. Finish first, second, working. Okay, good. Thank you, Justus. Next is Alexandra.
I finished the first graph. I'm just working on the second one and the third one.
Okay, thank you. Benjamin? On the third? Okay. Okay, so next is Elizabeth Castellano.
I'm working on the second one.
Okay, good. So you plot the first one. That's good. Next is Natalia Cordoba. Finish the first and now work on second. Okay, thank you. Benjamin's the third. Okay, next is Jacqueline Delgadillo. Jacqueline is not here, right? Next is Jenny.
I'm on the third one. Could you please show me how you did the third graph?
Okay, so how to plot the third graph? Okay, so let's see. Here you go. The third graph. Okay, so you want to plot the inverse. See that? It's this column here that you want to plot the inverse of the multimeter and the inverse of the sum. Okay? Those are the two columns that you want to plot.
Okay, thank you. Got it.
Okay. And next, Valerie. Yes, did you plot the first graph, Valerie?
Yes.
Okay, the second?
No.
Not yet working, right? Working on the second, okay. Next is Juan Escalera. The first graph, Juan. Let's see, Monte. Yes, did you plot the second one? Yes? What about the third one? Are you working on that or plotting? Oh, you finished, okay. If you finish plotting all the 3 graphs, right? So start working on the units, right? So Bianca. Did you plot the first graph? Bianca is not here. Yeah, looks like Bianca left, huh? Okay, let's write it down left. Next, Edwin Gonzalez. Did you plot the first graph, Edwin? Looks like Edwin's away from his computer. Oh, okay, good. You plot. What about the second? Second graph, did you plot it? Working on it. Okay, thank you. Next should be Eli Gonzalez.
Yes.
You plot the first. What about the second?
Yes.
Yes. The third?
Yes.
Yeah. Okay. Okay. So you finished. Okay. So what about the units? Start working on the units. Did you finish the units already?
No, I'm just trying to decide how to do the 1/over units, but I think I've got those too.
Okay. I'm gonna put your working on that. Just say Monte. So okay. Okay. So okay, I'll get back to you, Monte, and let's go here with Manuel. Manuel, are you there? No, Manuel apparently left. Samantha Hubert, are you there, Samantha?
Yes.
Okay, so you finished the first one. What about the second one?
Working on it.
Okay, thank you. Let's go for the next one. CJ, did you finish the first graph, CJ? Hello, CJ.
You can hear me?
Yeah, I can hear you. Okay.
Yeah, for the first graph, I finished it.
Okay. What about the second?
Second one, yeah.
Yeah.
For the third one, I'm working on.
Okay, thank you. Luis Leal, let's see. Luis Leal is not here. Next is Amber Lopez. Did you, Amber is not here either. Let's see. Yeah, it looks like Amber left, huh? Okay, Amber left. Arely Lopez.
Yeah, I finished the second graph, and I'm working on the third graph right now.
Okay, thank you. Genesis. Hello, Genesis. Did you finish the first graph?
Hello? Yeah, I did the first graph. I'm still working on the rest.
Okay, on the second, right? Okay, good. And Mary?
I did the first graph, working on the second.
Okay, thank you. Galia? Working on third. Okay, good. So Y and Y, let's go. Ramon Olivares. Ramon is not here. Okay, next is Taylor Farm.
I finished the first one. I'm working on the others.
Okay, thank you. Next is Jeremy Pittman. I don't see Jeremy here, right? So next, Stephanie Hammonds.
I plotted all three graphs. I just need to label and do the I just have to fix all of them. That's it.
Okay, so you're working on all the three, right? Is that right?
Yeah.
Okay, good. So you first plot, and now you're working on the axis, right? On the label of the axis. That's what you're doing, right?
Yeah.
Okay, thank you. Stephanie Ramos.
Oh, that's me. That's what I was saying.
Oh, that was Stephanie. Okay.
Yeah.
Well, wait a minute. Okay, I'm reading the wrong one. Thank you. Leslie Rios.
I did the first one and the second one. I'm just working on the third in the units.
Okay, so you're working on the third one, right?
Yeah.
Okay, thank you. Jason?
I did the first and third one, but could you show me how to do the second one again? Sorry.
Okay, you did the first and the third one. What about the second?
I'm working on it. I need to see how to do it again.
Okay, do you need any help with the second one?
Sorry.
Do you need any help with the second one?
Yes.
Yes, okay, so let's see. The second one, well, the second one is what? Just those two, okay? That's the second graph. Just those two columns, right? See the third table and insert chart, you know, and then, should be straightforward, right? So here you go, trend line, right?
Okay, I see. Thank you.
Right.
Is it the left column first, then right column second, or is it right column first, left column second? Sorry.
Doesn't matter either way. So you can do first column, left column first, or you can do right column first. Doesn't matter.
Okay, thank you.
And 12:40, we are running out of time. Let's see. Hema, did you finish the first graph, Hema?
Yeah, I'm done with all the graphs.
Oh, all the three. Okay. So did you start working on the units?
Yes.
Okay, so you're working on the units right now, right? Okay, so, and after the units, you work on sig figs. And after the sig figs, you work on the CL, right? 12:42 right now. Let's go back here. Abir, are you there? Abir, okay, looks like Abir left, right? Left, and Nestor, did you finish the second graph?
Yeah, I finished the second, but I'm working on the third.
Okay, thank you. Monte is back, right? Monte, did you
I'm here. I'm currently working on the second one.
Okay, good. So did you finish the second one?
I'm currently working on the second one.
Did you finish the first one?
No, not yet. I'm working on it.
You're also working on the first one?
Yeah, the first one is done.
The first one is done. Okay. So you were able to download their spreadsheet. Okay, good. So Isabella, did you finish your third graph?
I'm finishing it up.
Okay. So what about the units? Did you start working on the units?
Yes.
Okay. Good. Next is Justice. Did you finish the third graph, Justice? Just finishing up now, working on units. Okay, good. Good. And Alexandra?
Still working on it.
On the third one and on the second one?
Yeah.
On the second, okay. Do you need any help with the second graph?
No, I'm all right. I'm just finishing up.
Okay. So Benjamin, finished third graph, working on the units. That's good. Next is Elizabeth Castellano.
I'm finishing up the third graph.
Okay. And that's good. So you finished the second, right? And working on the third. Okay. Natalia Cordoba. Finished third graph. Okay. And working on the units. That's good. Jacqueline is not here. Next is Jenny.
I'm just working on the units.
Okay, good. Work on the units and you finish the third graph. Okay. And Valerie?
Yes. Oh, I finished all the graphs.
All the
I'm
graphs?
working on the units too. But I was wondering if it was units for the table or you meant units on the chart or the same.
Let's see. Let's take a look at the units. Oh, on the chart as well, right? Should be the units on the table and the units on the chart, right? Okay, units goes here, right? Goes here. Let's see where the units go. Here, 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 and note, see that for this last table, no, you want the one before the last table, the units is going to be the inverse of ohms, right? Here's going to be the inverse of ohms, the inverse of ohms, and here the inverse of ohms. Only here that's going to be ohms, right? And here is going to be the inverse, right? Because I'm dividing the resistance by 1. Okay, that's this one is a little bit tricky. Okay, and those same units should go on the graph as well. Should go on the labels of the axis. Next, Juan Escalera. Hello, Juan, are you there? Okay, working on the units and sig figs. Okay, thank you. Next, Bianca. Bianca left, right? Edwin Gonzalez, 4 more minutes to go. How are you doing there, Edwin? Did you finish the second graph?
Yeah, I'm moving on to the third.
Okay, working on the third. That's good. Eli Gonzalez.
Finished with the units and sig figs. Yeah.
Okay, so we're working on the units and sig figs. Okay, and next is Manuel Hernandez. Okay, Manuel left. Next is Samantha.
I finished the second. I'm moving on to the third.
Okay, thank you. CJ. Hello, CJ. Okay, I can't hear you. Okay, I'm gonna put a star under your name here, and Luis Leal is not here. And Amber Lopez doesn't, Amber's not here. Arely, did you manage to finish the third graph? Arely, it doesn't look like Arely is here. Yeah, looks like Arely left. Okay. Next is Genesis. She working on the second graph or the third graph? Okay, on the second graph. Okay, good. Mary?
I finished the second. I'm working on the third. Can you show the third one more time?
Yeah, let's go there. Here you go. Third one is this one right in here, right? Should be this one and this one, okay? So you highlight this one, those numbers, and highlight these other numbers. It's the inverse. This one is going to end up in the x-axis. This one is going to end up in the y-axis. You know, insert. Here you go. That's what we get. Okay? Make sense?
Yes, thank you.
Hold on. Next. Galia. Working on units. Okay, that's good. W and Ramon. We're running out of time. Okay, so I think you can do the rest by yourself, right? Don't forget that. Here you go. I'm gonna write that down here for you. The sig figs of the nominal values color code. You have only two sig figs, okay, for the nominal values color coded. Okay, the remaining sig figs are either obtained from the sig fig table, or obtained from the rules for addition, division, and multiplication. Okay. Okay, it's 12:51 right now. I understand that you can finish on your own, right? And I'll post on Canvas when this lab is due. Okay. Since we are going to have a big vacation here, and then after the vacation we're going to have the exam, I'm thinking about make it due after the exam, after the second exam. So thank you for being here, and I see you again on after the spring break, right? Thank you very much.
Enjoy your spring break, Professor.
Yeah, you too. Enjoy.
Thanks, Professor.
Right?
See you after spring break.
See you.